All right, so we'll continue here. Going on with our t-test. So I know I spent a lot of time talking about our selection of alpha and whatnot. And there's not even going to be a whole lot of homework problems on this, but this is all important information that you need to know, and will probably show up, make an appearance on the final exam here. So keep that in mind. Okay, so let's talk about t-tests some more. In our first t-test that we did, our alternative hypothesis had a not equal sign. So we did what we call a two-tail or non-directional test. Two-tail or non-directional test, and that involved doubling our tail area to get our p-value. Sometimes our alternative hypothesis does not have a not equal sign, okay? So if the alternative hypothesis has greater than or less than, we do a directional test. And so in these situations, okay, well I should say, just on a side note, the null hypothesis always has an equal sign. Okay. So the null hypothesis will always have an equal sign. So in these situations, the null hypothesis might be something like mu1 is equal to mu2, and the alternative might be mu1 is greater than mu2. And so in these situations, we are only interested if we have evidence to show that mu1 is larger than mu2. We are not interested if mu1 is smaller than mu2. Okay? So in these situations, we are only interested if our data supports mu1 greater than mu2, and not the other way around. Okay. So for example, maybe you're testing to see if a new medication reduces blood pressure. In that case, we're only interested if the results show that the blood pressure after taking the medication is lower than what it was before. Okay? If the data goes the other way, then our medication is worthless. Okay? It's not of value to us. So here we want to know, if we're testing blood pressure medication, we want to make sure that the after blood pressure is lower than the before blood pressure. And if that's not the case, then there's no point in testing to see if the difference is significant or not. We just know our blood pressure medication doesn't work. So in these cases, we do a directional test. So directional tests are done in a very similar way to a non-directional test, except that in the beginning, you have to check to see if your data supports the directionality. So we do something called a directionality check. So prior to doing any math, we do a directionality check. So if the alternative hypothesis says mu1 is greater than mu2, then in our data, y bar 1 has to be greater than y bar 2. Okay, then in our data, this should happen. So in our data, our sample 1 should have a y1 bar that's larger than y2 bar. Okay? If the alternative says this, then this should be true in our data. If this is not true, then there's no sense in going forward with the test. Okay? If this is not the case, then our data will provide no evidence to support the alternative. Okay? Remember, we're always using our data to see, does it support the alternative or not? Okay? Do we have enough to reject the null or not? That's how we're using our data. We're not using our data to support the null, we're using our data to see if we can support the alternative and reject the null. So if this is not the case, then we will have no evidence to support the alternative. Okay. So but if it passes the directionality check, meaning the alternative says this and your data matches that, then yes, go forward with the test in the same way. Okay? If it passes the directionality check, continue on with the test. Yes?
In the directionality check, is that y bar 1 is greater than y bar 2?
Yeah, if your alternative says that mu1 is greater than mu2.
Okay.
If your alternative says the opposite, mu1 is less than mu2, then y bar 1 in your data should be less than y bar 2 in your data.
Okay.
So you just want to make sure that the data goes in the same direction as your alternative hypothesis. Okay? Otherwise, there's no point. Because we're always, when we're doing these tests, we're saying, is the difference we observe statistically significant? And does it support the alternative? And if our data doesn't even go in the same direction as the alternative, then there's no point in continuing on. So if it passes the directionality test, then continue on with a directionality check, then you continue on with the test. So you find your test statistic, which would be, y bar 1 minus y bar 2 over the standard error. Look up in the t-table to get a tail area. And then you do not double the tail area. Your tail area is now your p-value. Okay, so in the non-directional test, we doubled the tail area to get our p-value. If it's non-directional, you just leave the tail area as is, and that is your p-value. So let's try an example. So maybe, alright, so you go to the grocery store. And they sell eggs, right? And these, and they sell large eggs and extra large eggs. I don't know, the extra large eggs maybe cost an extra 10 cents a dozen or 20 cents a dozen or something like that, okay? So maybe you're like, oh, I wonder if the extra large eggs actually are larger than the large eggs, okay? So we'll say, you know, do the extra large eggs actually weigh more than the large eggs. Okay, I have no idea what is the average weight of an egg. Let's ask Google. Average weight of an egg. Chicken egg sizes, Wikipedia. Go. Oh, look at this. Okay. 64 grams, 57 grams. Okay, so let's say you buy some eggs at the grocery store and you weigh them all. Okay, so we have sample 1. Sample 2. Okay. Alright, so our null hypothesis is, let's say this. Okay. Our null hypothesis will say mu1 is our large eggs. So our null hypothesis is that the average weight of these eggs are the same. Mu1 equals mu2. And the alternative would then be what? We're asking, do the extra large eggs actually weigh more than the large eggs? So we would expect mu1 to be less or greater than mu2. Less, okay, because mu1 corresponds to the large eggs. Okay, so let's say you took a dozen eggs, and we'll assume that these are random samples, okay? So what is our first thing to do?
Directionality check.
We have to do a directionality check, okay? And so we do our directionality check, and what happens here? Does it pass or not pass a directionality check?
No pass.
Does not pass. Why? Because when we look at our data, it seems, if anything, that the large eggs are actually bigger than the extra large eggs. Okay, so our directionality check, we do, y bar 1 versus y bar 2, and we have 61 is greater than 60, so it does not pass. Okay, so then what would our conclusion be?
That they
Extra
So
large.
we would say we have no evidence to support the alternative. So just based on the directionality check, we can say a few things. We have no evidence support the alternative, okay? We do not reject the null. And what would our p-value be? It's a little odd. So the p-value is the probability of observing our data or something more extreme if the null hypothesis is true. Okay, more extreme now applies to what the alternative says. So more extreme means what's the probability of getting our data or something more extreme where mu2 is larger than mu1. So in this case, well, whatever it is, okay, because we did not reject the null hypothesis and we didn't pass a directionality check, our p-value is going to be over 50%. Okay? So anytime you fail the directionality check, your p-value is over 50%. Because we're asking, what's the probability of observing our data where we're getting basically a difference where sample 1 is 1 gram larger, but we're looking in the opposite direction. So our p-value is larger than 50%. Okay? But basically, if you fail your directionality check, all of these things are going to hold true. Okay? You're going to have no evidence to support the alternative. You do not reject the null hypothesis, and your p-value is going to be over 50% if you fail the directionality check. Is that okay? Okay, so let me change the data. Let's say, oh, I realized I grabbed the wrong carton of eggs, and I thought it said extra large, but it actually just said large. Okay, so now I go back. I say, whoops. Let me get a real, what do you call it, carton of eggs? Think that are extra large eggs, and let's say it looks like this. Okay, so based on these 2 dozen eggs, do we have evidence that the extra large eggs are bigger than the large eggs? Okay. So we do our directionality check, and what happens there? It passes the directionality check, okay? And we find that y bar 1 is less than y bar 2, so it passes. Okay, so then we have to go forward with the math behind the test. So I'm going to erase my hypotheses. So my test statistic would be what? Y bar 1 minus y bar 2 divided by the standard error. What is my standard error? 3 squared over 12 plus 3 squared over 12. .22. 1.225. So my test statistic is 61 minus 64 divided by 1.225. So I get negative 2.449, or negative 2.45.
61 minus
65.
Oh, I'm sorry. I messed that up. Okay, my test statistic is even greater. Sorry. I get negative 3.26. 0.65. Alright, how many degrees of freedom would I be looking up in the table? We'll look up 20 degrees of freedom. No, 22 degrees of freedom, sorry. I'm a mess. Okay. So we look at 22 degrees of freedom. And what is my tail area? Degrees of freedom, my test statistic is negative 3.265. I'm getting between 0.005 and 0.0005. Is that okay? So looking at extra large eggs versus the large eggs, this is what I get. So my test statistic is negative 3.265, and so my tail area is 0.005 and 0.0005. So my p-value, my tail area is my p-value. Okay. And so let's say I'm using alpha as 5%. How does my p-value compare to alpha? Yeah, my p-value is much smaller than alpha. So what do I conclude? Yeah, so I reject the null hypothesis. Okay. And I say the probability of seeing a dozen eggs where the average is 65 and a dozen eggs where the average is 61 and getting a 4-gram difference. The probability of seeing a 4-gram difference from random chance alone is so small that I'm going to ignore it. And I'm going to come to the conclusion that the average weight of extra large eggs is indeed greater than the average weight of large eggs. Okay, reject the null. We said we have evidence to believe mu1 is indeed less than mu2. Yes?
So when the alternative hypothesis doesn't have greater than or equal to signs, you do the two-tailed test?
Yes, so if it has a not equal sign, it's a two-tailed test.
Okay.
It's either going to be greater than, less than, or not equal.
Okay. And if you do the two-tailed test, the p-value is equal to two times
the tail area.
Tail area, okay.
Two times. Does that feel okay? Okay.
Is this called the one-tail test, or?
Yeah, this is called a one-tail hypothesis test or a directional hypothesis test. Okay. Yeah, call it one-tail or directional test.
How did you get your test statistic again? Like when you HGT?
So I'm looking at my observed difference. So I'm looking in my data, the observed means and the difference between them, and I'm comparing that to the standard error. So I'm just doing 61 minus 65, and I get my standard error by doing S1 squared over N1 plus S2 squared over N2. Right? They just happen to be the same set of numbers here.
But your how'd you get your over 0.05?
Oh, yeah. Okay. So when I go to my, I'm going to just go ahead and erase this. I go to the t-table, alright, and I'm just gonna, looking at the row 22 degrees of freedom only, okay, I'm just gonna copy the numbers towards the right end of the table. Okay, so in that row 22 degrees of freedom, I've got 2.508, 2.819, and 3.792. And these correspond to 0.0005, 0.005, and 0.01. Can you see that in your table? So I'm looking at the value 3.265. I'm just going to ignore the negative sign because it's symmetric. Okay? So 3.265 fits in between these two numbers, 2.819 and 3.792. And I know if I had 2.819 exactly, the amount of my tail is 0.005. And if I had 3.792 exactly, the amount of my tail is 0.0005. Okay? I don't have either of those numbers exact, so I do know that the amount of my tail will have to then be between these two numbers. Okay, and that's all. Yes?
I'm just a little confused. I mean, it says that rejecting the null is the data is large enough and did not happen by random chance alone.
That the difference in our data is large enough that we consider it statistically significant. So basically, you know, I took a dozen eggs, a dozen large eggs and a dozen extra large eggs, and I took the average weight of the large eggs, 61 grams, average weight of the extra large eggs, 65 grams. So I have a 4-gram difference. Is that 4-gram difference statistically significant or not? Okay. When we go through the math, we get, you know, this test statistic and we get this tiny p-value. That tells us that difference is large enough for it to be statistically significant.
So that is, I thought that was a small number between 0.005 and
So
0.00.
the difference is the 4-gram difference. The 4-gram difference is large.
Yeah.
Okay? The 4-gram difference has a small probability of happening by random chance alone. Okay? So if there really was no difference in all of these eggs, okay? By random chance alone, it's possible for me to get 12 eggs where the average is 61 and 12 eggs where the average is 65. It's possible for that to happen from random chance alone. But what's the probability of that happening? That probability is incredibly tiny. Okay? The probability of that happening is incredibly tiny. So rather than saying, you know what, I probably just got really, really lucky with these highly unusual eggs, rather than saying that, I'm going to just say, oh, well, that would give me reason to believe that they're not coming from the same pool, that there is a difference in the populations. Okay? Yes?
When we calculate the test statistic,
Uh-huh.
that's the value, those are the values in the t-table.
It's the value that you would look up in the t-table
In the t-table.
to get the probability associated with the test statistic.
Is that the same thing as the t-score in the confidence
Yes,
intervals?
yes,
So
yes.
it's the t-score.
Okay, so in the confidence interval you are, it's like a different approach, but it's a similar idea. Okay, so you're using a t value that you find in the t-table. Okay. All right. Eric, did you have a question or?
Yeah, I was going to ask you, so the negative sign, is that, and you already answered it, doesn't really tell us much as far as subtracting from one or anything of that sort, right? It's just
Right.
same
We're
value.
not really subtracting from one because we're always just looking in the tail. Okay. The negative sign, I guess, matters when you actually do the directionality check. But rather than talking about pluses and minuses for the directionality check, I'm just saying look at the data to see if it matches what happens in the alternative hypothesis. Okay. Yes?
And the
I just wanna make sure I'm clear with the directionality check. If it doesn't pass, then we can just stop there and we know that, that we're not rejecting the null hypothesis.
Exactly.
Okay.
Okay, so if it doesn't pass the directionality check, you're not gonna have any evidence to support the alternative. Okay? Alright.
Is there a time that your p-value will straddle your significant level, like your 0.05?
You know, in a very rare circumstance, it is possible, okay? Like in a rare circumstance, you could get your critical value to be, you know, like if we were doing 22 degrees of freedom, it's possible that your test statistic ends up being exactly 1.717, meaning your tail area is exactly 0.05. That is possible. It happens rarely, and depending what textbook you read, they'll say if your p-value actually is equal to alpha, then you should reject or you should not reject. It's a little it's ambiguous, okay? And you know, again, we set these rules where it's like if it's bigger than alpha, you reject. If it's smaller than alpha, I mean, if it's bigger than alpha, you don't reject, and if your p-value is smaller than alpha, then you do reject. It's not meant to be the end-all, be-all of be-all, end-all of what to do. Okay, that's the process that we go through, but it just means the probability of seeing your data or something more extreme is actually equal to 5%. What do you do with that? It's up to you, really. Okay, your choice of alpha is technically up to you also, so you can choose. I think a lot of textbooks would say to reject at that point if your p-value is, well, it depends. So I don't know, but it doesn't happen very often. Okay, but it might. Yeah. Okay. I mean, I suppose if you selected odd alpha significance level of like 15%, then yeah, your tail area could be between 10 and 20%, and then you don't know what to do. But I would say that's kind of a poor choice of significance level if you don't have a defined line there. Okay, let me keep talking here about how confidence intervals relate to our t-test, hypothesis test. Okay, so at the end of chapter 6, we used confidence intervals for a difference between means. And do you guys remember the conclusion there? We said if the confidence interval looked like this, then we had a difference that there was means. And what would the confidence interval have to look like?
Not include 0?
Not include 0, yeah. So when we created a confidence interval for mu1 minus mu2, if the confidence interval did not include the number 0, then we said we had evidence that there is a difference between means. Confidence interval for mu1 minus mu2, okay? And the conclusions were, if the confidence interval does not contain 0, then we have evidence that there is a difference. And if the confidence interval contains 0, So this part should be reviewed. Okay, so if the interval for the difference contains the value 0, then we don't have evidence that there's a difference because 0 is a potential value for the difference between mu1 and mu2. On the other hand, if the interval is entirely positive or the interval is entirely negative, meaning there is no 0 between the ends of the interval, then we do have evidence of a difference. The conclusions from a confidence interval will match the conclusions made from a hypothesis test. Okay, so a non-directional. So when we're talking about hypothesis tests, we're only talking about non-directional hypothesis tests here. So meaning the alternative has a not equal sign. Okay. So the conclusion of a hypothesis test matches the conclusion from confidence. Okay. So a hypothesis test, a non-directional or two-tail, meaning the alternative has a not equal sign in it. A non-directional hypothesis test, or t-test, with significance level alpha will have the same conclusion as a confidence interval with basically 1 minus alpha % confidence. So if you do a 5% hypothesis test with significance level 5%, alpha equal to 5%, that's equivalent to doing a 95% confidence interval. Or if you're using alpha is 10%, it's equivalent to what level of confidence? 90% confidence interval. Okay? So the conclusions from a 90% confidence interval would match that of a hypothesis test with significance level 10%. Okay? Alright, so let's try some thinking challenges out here. So let's say we perform a t-test, non-directional, with alpha equal 0.05. Okay. And the data has us conclude that there is a significant difference So what does this tell us about our p-value?
Small.
Smaller than what? Smaller than 5%. Okay. So let's say what if I use the same data doing with a non-directional test, again, and I use alpha equal to 10%. What would my conclusion be then? Would I conclude to reject the null, not reject the null? Don't know.
Data's still significant.
Yeah, so whatever I did here, okay, the only thing that changed is alpha. Would my data change? No, I'm using the same data. Does my test statistic change? My p-value that I come to at the end? Does that change? No, that's all the same. The only thing that I'm changing is alpha. So over here, whatever my p-value was, I don't know, but I do know my p-value is less than alpha, less than 5%. So if I come down here and I do the exact same test, my p-value is still less than 5%, but now I'm using alpha as 10%, so my p-value is still less than 10%, or still less than alpha. Okay, so my p-value, so from here we know that the p-value is less than 0.05, okay? And so here our p-value is still less than alpha, so we still conclude to reject the null hypothesis. Okay? Alright, same question, but what about with alpha equal to 2%?
Depends on P. So,
Yeah, here we can't tell. Okay? Now we cannot tell. We can't tell without knowing the p-value. Yes?
When you say non-directional, does that mean it fails directionality?
No, non-directional means the alternative hypothesis has a not equal sign. That's what non-directional is. Okay, it's a two-tailed test. It means the alternative hypothesis has a not equal sign. Okay, so we can't tell without knowing p-value. Is that okay? All right. Keep this part still in mind. So we perform a test, non-directional test, with alpha equal to 5%, and the data has us conclude that there is a significant difference. Okay, if I made a 95% confidence interval with the same data, would the confidence interval contain 0? Yeah? No? so think about it, don't shout out your answer.
The data where alpha equals 0.02?
No, so this part remains the same. Okay, so we're performing a t-test, non-directional t-test with alpha equal to 0.05, and the data leads us to conclude that there is a significant difference.